Hello, Mom Aubrey here, and welcome to the discussion on the Earth's four systems. We have already discussed the formation of the Earth in specific detail. Now let's go ahead and discuss the composition of Earth. So back in class, my students would say that it's like the four elements avatar, but instead of fire, you replace it with your life or your biosphere. So I know these terms are very familiar to you, so this lecture would only serve like a review of what you already know. So we have four spheres or four systems: atmosphere, hydrosphere, biosphere, and your more aptly termed geosphere. So there are certain scientists that would like to look at Earth and study Earth as a whole, so Earth science. But there are certain scientists that would prefer to look at the certain systems of Earth and how they are interacting with one another, and that's Earth system science. So in Earth system science, we divide our planet into four groups. You have your atmosphere, biosphere, geosphere, hydrosphere, as I mentioned. But despite being separated into systems, we have to acknowledge that they are still part of one planet and they interact with one another greatly. So, for example, the geosphere is the vast majority of our planet, but it holds the hydrosphere. Then the biosphere, here on the crust, our life zone, greatly depends on atmosphere, geosphere, and hydrosphere to survive. And of course, the atmosphere is held up by the gravity of the geosphere. And also, interacting with atmosphere and hydrosphere in weather and climate. So all of these separate systems, you can consider them separate systems, but they will have an effect on one another. Okay, so when you are studying Earth science, there are certain terms that you have to know. You have open system and your closed system. So when we are talking about open system, energy and or matter move in and out. Then if we are referring to a closed system, no exchange of energy and matter with its surroundings. So we will look at Earth as one system and try to identify, is the Earth an open system or closed system? In terms of energy, well, that depends on the type of energy. So we have your non-renewable energy, your oil, your coal, all of that is contained within the Earth. So it's a closed system. The only open system we have is when we are looking at solar energy. So part of the sun's rays are moving into our planet, but the solar energy is also reflected out of the Earth, ideally. So that's the problem with when it comes to greenhouse gases, because it stops the planet from reflecting the excess solar energy back into space. So that's why we shouldn't have greenhouse gases or reduce our greenhouse gases. So for solar energy or energy from the sun, it should be an open system for Earth. But for other energy and matter, it's a closed system. So everything that is within the Earth, the resources, the energy that we have, that we consume, is within the Earth. Same goes with the waste that we produce. So all of it is still a closed system. So essentially, Earth is a closed system. That's why it's very important to study their interaction. So this is the open system of energy in terms of sunlight, solar energy that I'm referring to. But for other forms of energy and matter, we are a closed system. And again, this is why it's important to study the different subsystems of Earth, because we are a closed system. A change in one system will definitely affect the other systems. Okay, so 4 subsystems that we have to go through. Let's start with the first one. So you have your geosphere. So as I said, this is the largest of the 4 spheres. And comprises the solid portion of the planet, extending 6,400 kilometers from the surface towards the core. So this is like a dissected diagram of the Earth. notice that the crust is like really, really thin. So when we are referring to the crust, this is the cooled down part of our planet, and that's more most of life, where all life rather is located. There are certain stories online that people dug into the mantle so deep into the earth that they reached the mantle. That's not true. We have not even reached the mantle yet. We are still at the part of the crust. It's so deep, and if you will compare the crust and the bulk of the mantle, wow, it's really, really thin. Crust is really thin in comparison to the rest of the planet. Okay, so of course your crust is the solid part of the planet, and it has two parts, your continent, or two types, your continental and oceanic crust. Okay, you have your moho, or the Mohorovisic discontinuity, so the boundary between the crust and the mantle. Okay, and then you have your liquid outer core, although a molten outer core would be a better term because it's semi-solid, semi-liquid that is moving continuously within our planet. And then you have your solid inner core. Okay, so other terms that we will go through as we discuss the slide. So again, the crust, the cold, thin, brittle outer shell, and it's only less than 1% of our Earth. And as you notice, it's made up of very light materials, your oxygen, mostly oxygen, and silicon. Okay, moving into the mantle, this is made up of hot ultramafic rock. So it has its own heat, and it is also heated up by the core itself, and it represents 68% of the Earth's mass. So we know the composition of our layers based on the studies on seismic waves. So more on that later. So it is mainly composed of oxygen, silicon, like the crust, but you have other heavier elements like magnesium. So although the top area of the mantle isn't completely molten, the soft mantle region flows. Okay, so I think I have a diagram here somewhere. Okay, so this part is specifically for discussing the upper part of the geosphere. So when we talk about the lithosphere, this is a combination of the crust and the upper part of the mantle, which is solid. So this lithosphere is what makes up your plate tectonics. So imagine that the Earth is covered by plates, and what happens is, since this part is solid, it will keep moving, because what is under that lithosphere layer is the asthenosphere. So the asthenosphere is the partially molten upper mantle, and it's like plastically and can flow. So it means like it moves around. It's like a thick material that is moving within our Earth, and that powers our plate tectonics. So if you can imagine like a thick material of rock composed of your crust and upper mantle, and then your lower mantle is still molten. That's why it's moving around, moving our plates as the planet of the planet. Okay, so that's your lithosphere and your asthenosphere. Okay, and then we have your core. So it's dense and metallic, and is mostly composed of iron, nickel, and is composes 31% of our planet. So we know that the core is metal because if you will study the meteorites that crashes on Earth, it should have pretty much the same composition of the Earth, and then you process it under a differentiation process. That will be the result, that the core would be the metallic material. Okay. So calculation indicate that the core is 85% iron and metal with 15% nickel metal. Okay, so how do we know, or how do we identify that the planet has layers? Of course, we have not dug into the mantle and the core. So how do we know its composition? So I already mentioned one, that we have studied the composition of the meteorites that crash on Earth. And just like an analogy, we compare it to the composition of the Earth. But how do we know that where the certain boundaries stop? Where does the crust stop and become the mantle? And when did the mantle stop and become the core? We study the seismic waves or the S waves. So whenever earthquakes are being produced or occur on Earth, it produces seismic waves, and that's something that scientists could study. Okay, so when you are studying seismic waves, there are two parts of seismic waves. You have your P wave and your S wave, and they behave differently. So let's say that the epicenter of the earthquake is here, and you can detect the behavior of the P and S waves depending on the material that they are passing through. So the S wave cannot pass through liquid. So what happens is, when these seismic waves try to move through the liquid outer core, only the P wave can pass through, which signify that the outer core is liquid. And then the P waves also behave differently here in the middle of the Earth. That means that there was a change in the material, and that's our basis of our layer differentiate of specifying layers of the Earth. The behavior of our seismic waves would help us predict or estimate the materials within our planet. Okay, so going back, the strong magnetic field caused by the convection or the movement of heat and magma in our liquid outer core. Yes, the magnetic field is caused by the convection of our liquid outer core. So we would have a magnetic field without that movement. Okay. Aside from that, the hotter inner core, because the inner core is very hot, because aside from being an originally molten material, you also have radioactive elements within it. So imagine molten material plus radioactive chemical processes that would result to a lot of heat. So that produces heat, which transfers to the outer core, which is molten, and also parts of our mantle. Okay, so the Mohorovicic discontinuity, or simply called the MOHO, is a particular part or the boundary of the crust and the mantle. Now, why do we call it a discontinuity? Because if we have seismic waves running through the crust and the mantle, this is the part wherein, let's look for that definition. At this continuity, seismic waves accelerate. So the materials, the seismic wave running from the crust to the mantle starts to speed up whenever it reaches the Mohorovicic discontinuity, or the MOHO. That is because the mantle is much thicker and denser than the crust. So naturally, the seismic waves would pass through the particles faster, making the seismic waves accelerate. Okay, so that's the logic behind the MOHO. Okay, so that should be everything for our geosphere. Let's move to the hydrosphere. So our hydrosphere, mostly what we know for sure is that most of the 70% of it accounts for 70% of the Earth's surface area. But there are propositions that parts of the mantle is actually has water as well, but we have not completely confirmed. Okay, but our hydrosphere is not limited to the water that we see on the surface. We know that there is also some groundwater that is still part of our hydrosphere. So just remember that everything that is part of the water cycle is part of our hydrosphere. So the rain that eventually fills up the land, the rivers, the streams, the lakes, the reservoirs underneath the ground, that's still part of our hydrosphere. Okay, so if we will survey the water that we have, 97% of the world's water is salt water. Okay, then 1%, only 1% all of the water on Earth is what we use daily or accessible to us. So 30% of the fresh water that is available on Earth is mostly locked in freshwater ice or glaciers, or it's deep underwater or underground. There has been propositions that in order to resolve water shortages in certain areas, we could tap with on that 30% groundwater, because there's so much, there's 30% groundwater. But the problem is it will affect the geosphere or the water table in general. So there are some reservations when it comes to tapping into groundwater. Okay, now our ice or glaciers are now starting to melt, and it's mixing with the world's salt water, so we can't really use that either. Now we are stuck with the 1% that we are dependent on. Okay, so that's it for the hydrosphere. Let's move to the atmosphere. And as you recall, it has several layers. So the atmosphere is a layer of gaseous envelope that surrounds the planet and then eventually expands into the surface. So if we will enumerate the parts rather, your troposphere, so the lowest part, stratosphere, mesosphere, thermosphere, and then exosphere. So TSMTE. 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 So troposphere, stratosphere, mesosphere, thermosphere, and exosphere. So the troposphere, the lowest part, and that's still within the layer of the clouds. So if you look up into the sky and you see clouds moving, that's still part of the troposphere. Above the clouds, however, is your stratosphere, and this is where our ozone layer is located. Moving into the mesosphere is a very cold area in our atmosphere. Then we have your thermosphere. So the thermosphere is where most of the solar energy is being absorbed by our atmosphere. That's why there is a drastic increase in heat. Okay, and then slowly our atmosphere extends into space called exosphere. As long as there is still air particles that is moving around in the Earth's orbit, that is still part of our exosphere. Okay, so the composition of our atmosphere is this. According to NASA, nitrogen is 78%, oxygen is 21%, argon 0.93, and carbon dioxide is 0.04%. I know in comparison to the rest of the gases present on Earth that carbon dioxide seems so small. However, that even small changes in the percentage of our atmosphere have drastic effects to our environment and causing climate change in general. So do not underestimate that 0.04%. Okay, so aside from the elements that I have mentioned here, we have some neon, helium, methane, krypton, and hydrogen just moving around in the atmosphere. Okay, so just taking note how there's so much oxygen in our atmosphere that it makes up our ozone layer, but most of that oxygen has been produced by cyanobacteria way back in history. So quite amazing if you think about it. Okay, so speaking of bacteria, we have your biosphere. So it includes all forms of life on Earth, including organisms within the Earth itself, or in the deepest part of the Earth, and the oceans, and up in the atmosphere. Okay, so even if these are four systems that are being studied separately from one another, again, they are very important, and a change in one of these spheres will affect the others. Okay, so they interact all the time. So for example, here, you have your Earth system subsystems interaction during a tsunami event. So during a tsunami event, you will see these three spheres interacting with one another. So a geosphere generates an earthquake which causes a tsunami, thus moving your hydrosphere. Then the hydrosphere will have waves, and these waves will hit the geosphere in the form of beaches and cliff sides, and will affect the terrain in general. The biosphere, of course, will be affected as well of a tsunami event. So they could threaten human life and other lives as well, and destruction of coastal communities. Okay, but in a normal situation, we as human beings affect these two subsystems. So we go in the hydrosphere to as a hobby, as leisure, as fun, entertainment, but we also depend on it to provide for our food and livelihood. Yeah, so just an example of Earth subsystem interaction. Okay, so that should cover all our learning objectives for this module. Okay, if you have any more questions, you know how to reach me. Don't be shy. Ask questions or clarification if you feel like you need to. That's all. Stay safe. Bye.